Yeah? But now, what is our unknown? What's that? Lambda. Yes, our unknown is lambda. Remember, somebody has given us a V naught, and our question is what eigenvalue looks kind of like V naught could be an eigenvector with that eigenvalue? There's a reason why we're solving this. We're going to come back to it in a second. Okay, so when I differentiate this thing, I'm just differentiating, actually this is easier, right? This is just a scalar function of one variable, lambda. Yeah, this is high school calculus. So in particular, we call this thing f of lambda, right? Then what is f prime of lambda? Well, this is a constant, so you get minus 2 v naught transpose a v naught plus 2 lambda mod v naught squared. Yeah? I think now this completes all of the possible derivatives we could have taken of this expression in CS to the y. Anyway, so in particular, what does this mean? Well, we can, we know that we want to minimize this thing, so the derivative is equal to 0. Yeah, and what comes out is lambda equals v naught transpose a v naught divided by mod v naught squared. Yeah? In fact, we already kind of knew this should happen, right? Because we've already talked about how finding critical points of this thing on the right-hand side, right? This looks like the Rayleigh quotient. Actually will give you eigenvalues. And now we're saying, in fact, it does better than that. The Rayleigh quotient when V naught isn't an eigenvalue, secretly is giving you the closest eigenvalue looking thing, right? So how could we use this? So if we're engineers, we're trying to think of numerical algorithms that are going to uncover eigenvectors and eigenvalues of this matrix A. Right? We now, during our iterative scheme, we have some guess for the eigenvector, which we've gotten just by whatever our iterative hammer is. And we're trying to find, and now we have an okay guess of the eigenvalue. And maybe now we fix our eigenvalue and we look for a better guess of the eigenvector. Yeah? Well, how can we do that? There's a strategy that's called Rayleigh quotient iteration that converges very quickly. And what is he doing here? Well, so there are 3 steps, right? All these algorithms are great. They're just like 2 and 3 liners. So the first step, we decided, even though secretly it's like this weird looking expression, really what it's doing is just finding the closest eigenvalue, or the closest thing to look like an eigenvalue if your eigenvector from the previous iteration is fixed. Yeah? So that's this number sigma sub k. Right? It's saying, if vk minus 1 were an eigenvector, what would his eigenvalue be? You see that? Okay. Now what do? Well, we know that now if the sigma k were an eigenvalue, then how could we find the corresponding, what could we do? Well, we could shift by this sigma k, right? It's okay, sigma k in reality isn't actually an eigenvalue, but it's close to the one we're looking for. So if we shift by that, then we know the one that we're looking for is close to 0 now. Yeah. So if I multiply by the inverse of a minus sigma ki, right, this thing should amplify the thing that's parallel to the eigenvector we're looking for. By a lot, because we just moved that number close to 0. And once 1 over 0, it's big. Yeah? So that's exactly what we do, and then we just normalize because we don't want to explode, just like normal, and we iterate this. So basically all this does is says we can do slightly better with eigenvalue iteration if we have a guess of what our eigenvalue is, because then we can move that guess to 0, right? And once we know that the guess is near 0, 1 over 0 is awfully big, and that's going to scale up the component that's parallel to this eigenvector the most, right? This is the trick of Rayleigh quotient iteration. And it converges very quickly. Now, as a mathematician, I'm excited by this. In fact, you can prove that the convergence rate of this is bounded by the conversion rate of the other guy. It does very well. It gets to this eigenvector very quickly. I don't have to hammer this inverse matrix too many times, which is good. But what did I lose? Right? So remember, before we were just hitting vk minus 1 with a inverse a bunch, right? We just kept doing that. Just kept, multiplying by inverse over and over and over again, and eventually we got the eigenvector with the smallest eigenvalue. But now we're hitting it with the inverse of a minus sigma ki. But sigma k is going to be different for each k, right? Each iteration we have a different v, we've got a different k, and so our approximation is kind of shifting underneath our feet, right? So remember the one trick for making eigenvalue iteration on that inverse of A, one trick for making that faster was to LU factorize A, and then use the LU factorization to apply A inverse a bunch of times. But I can't do that anymore. Right? Because now, every time I apply an inverse, it's a different inverse. It's an inverse of A minus sigma ki for different sigma k's. And if you kind of play with it, you'll notice that LU factorizing this thing is not particularly related to the LU factorization of A. It's really a depressing fact about mathematics, that all you can do, if you mess with the diagonal of a matrix, can completely change the way LU factorization goes. So what does that mean? Well, that means that each iteration of Rayleigh quotient, of this Rayleigh quotient algorithm, can take n cubed time, right? Whereas each iteration of this inverse algorithm took n squared time, right? Because we put all the n cubed into factoring n. Yeah? So there's a really weird trade-off that happens here, and this is where engineering and numerical analysis start to interact, right? Because what's going on is this: inverse iteration is going to take more iterations. It doesn't converge as quickly to the eigenvalue you're looking for. But each iteration is only n squared time. This algorithm numerically takes fewer iterations, but each iteration can take n cubed time. Right? So something you have to do as an engineer is to decide which of these strategies is faster for the eigenvalue problem you're trying to solve. And unfortunately that's different for different matrices A. Right? For example, the Rayleigh quotient iteration just happens to converge ridiculously quickly, like only take 5 iterations as opposed to 5 billion, right? Then that n cubed versus n squared might not be such a big deal, right? But if it's a difference between like 5 and 7 iterations, then it might. Right? So this is kind of where CS 161 goes to die, right? Because now we can't just calculate operations, we also have to figure out how those operations interact with our convergence rates of our numerical stuff. And that is a very difficult problem to understand. Yeah?
We start with a randomly initialized eigenvector?
Yes.
Okay.
Well, be careful, a randomly initialized vector. It's not an eigenvector. Smack with it a bunch of times. Yes?
So I'm just going back on a high level, so we're guessing a lambda that's close to 0.
Not quite. So we're guessing a lambda that's close to what we think is an actual eigenvalue, right? And that, remember, that's why we solved this optimization here. It says if V naught is fixed, what is the lambda that makes this look the most like an eigenvector? And then we say, okay, once we have that lambda, we're going to call that sigma k. Now, we're going to say, well, that means that A minus sigma ki has an eigenvalue close to 0, right? Because I just shifted it by sigma k. Right? Sigma k kind of looks like an eigenvalue.
Yeah. Okay.
And so that means that it's probably going to be the biggest eigenvalue of this new matrix by a lot, because the eigenvalues of the inverse of this thing look like 1 over the eigenvalues of this guy, right? 1 over 0 and 1 over things close to 0 third part. This is the one time in life where you actually do want to divide by 0, right? Because that's going to multiply the biggest eigenvalue of the inverse by a lot, right? And that's what we want, right? We want a fast convergence of this expression. Cool? All right. Cool, so what do we have so far? We have strategies for finding one eigenvalue, and different strategies for depending on which eigenvalue we want, right? So if we want the biggest eigenvalue, literally all we have to do is just take a vector and start hitting with our matrix over and over and over again, and eventually we'll get the biggest eigenvalue, right? World's easiest algorithm. How do we get the smallest eigenvalue? Oh, well, we do the same thing with the inverse of the matrix, which if we've already implemented Gaussian elimination is also really easy. And how can we size just individual eigenvalues? Well, we can use this shifted matrix A minus sigma k. So that's where we are right now. But in the end, we might want more than one algorithm, or more than one eigenvalue. And by that I don't just mean like the biggest and the smallest, right? Maybe I want the 2 biggest. And I'm hosed. I haven't told you how to do that. So let's figure that out. So, returning to, I'm sorry, I forgot your name again. Right, that's right, I forgot your name. Well, Frank, you're going to have to write this down for me. So remember, we asked this question, which is, what is V0? Right? It's an excellent question to ask. And I told you we could just randomly initialize V0, right? Because it doesn't really matter, actually, right? I just write it as this linear combination, then we're just going to start killing things that don't look like the biggest eigenvalue. But there's one exception to this. In particular, what happens if V0 just happens to not have any component parallel to x1? It could happen. Right? And no matter how hard I hit it with A, right? No matter how many times I iterate power iteration, I'm never going to be able to amplify this component because it's just not there. Right? This is 0. Now, what are the odds of this happening? This is actually what like measure theory was made for. The odds of randomly choosing a vector that happens to have no component parallel to x1, the odds of that are exactly 0. But it is possible. Yeah? This is why probability is weird, right? It is so unlikely that this C1 is 0 that the odds of just picking a random number and having it happen to be parallel to x1 are approach 0, I suppose is one way to think about it. They're measure 0 in the set of things you might randomly draw for any reasonable random number. But it could happen. And the question is, well, then what? Well, then you're a little bit in trouble with your eigenvalue iteration, right? So usually implementations of eigenvalue iteration don't really care about this fact a whole lot, because again, the odds of it actually happening is 0. But yeah, so there's our question. But let's turn our bug into a feature. So in particular, actually, before we get there, what happens in that case? So let's say that this thing is 0, right? So now, what is going to dominate when I run eigenvalue iteration? The second biggest eigenvalue, right? Because that's what's left, right? The first biggest eigenvalue is just not parallel to this thing that we started with at all. No matter how many times I hit it with A, it's just never going to get there, right? So the first guy that has a non-zero component parallel to that eigenvalue is the one that's going to get amplified the most, right? And so what if I wanted to find the second biggest eigenvalue of M? How could I do that? Well, I could compute the eigenvector and eigenvalue, the biggest eigenvalue, right? Just using power iteration. And now I can start power iteration over, but before I do that, I project the biggest eigenvalue out of V0. Do you see? This is a trick, right? So the odds of randomly choosing a V0 with no component parallel to the first eigenvalue, or eigenvector, is the odds of that are exactly 0, but I can force it to happen by just removing this C1, right? So once I know x1, I can just remove this component, right? We have a formula for projection. Remember we covered that in our discussion of QR factorization. Yeah. So here's an algorithm for finding all the eigenvectors of A, at least when A is symmetric. What do? Well, we compute I guess in today's notation that should be an x1, but whatever. I compute the eigenvector with the biggest eigenvalue, that's x0 here, just by power iteration, just by hitting with it a bajillion times. Then I go back to my initial starting point, right, this v that I just chose randomly, and I project that x0 out of it. Right? So now v, no matter how many times I hit it with a, cannot amplify that component, because it's just not there. There's nothing to amplify, right? Hopefully you guys are very quiet today, but hopefully you're following. No matter how many times I hit this thing, this guy projected out, it'll just never get bigger, right? So what comes out next is the second biggest eigenvalue, yeah? And the second biggest eigenvalue. How do I get the third one? Well, now I go back to my starting point again, I project the first two guys out of it, and I run power iteration a third time, and now I get the third biggest eigenvalue, and so on. Right? This is a perfectly legitimate algorithm for finding the eigenvectors of a symmetric matrix M. Now, why do I say symmetric? What property did I use here by accident? Well, there are only like two properties we have for symmetric matrices, and one of them is that the eigenvectors are orthogonal, right? So if the eigenvectors weren't orthogonal, then what would happen? Well, I could project it out, but then somehow accidentally by amplifying one of the other eigenvectors, I might give a component of the biggest guy. So some kind of funny things can happen in that case. The proofs are a lot harder. Anyway, it's just good to know. But if you have a symmetric matrix, and basically all matrices are symmetric in my life, and by accident in your textbook, yeah, this is certainly a valid algorithm, but very easy to implement. Yeah? Now, Of course, there's a small problem that's lurking here, which is if I'm using IEEE, IEEE 1997, whatever the heck, floating point precision, and I multiply A times X, did I actually get A times X out? No. Right? Yeah, at least shake your heads, you don't have to say anything. Right? Because what happens when I multiply matrices is I'm subject to rounding and all these numerical problems that we talked about on day 1. Right? So there's this numerical creep thing that can happen. Right? But remember, what is my algorithm? Once again, for eigenvector iteration, we just keep hammering B with A until you get something that's parallel, right? But what could happen is A times B might have some itty-bitty component that's parallel to x1, right? Because accidentally, when I did a little bit of rounding, I rounded and I got just a tiny little bit off that's parallel to x1, right? But then what happens? I want to exponentially magnify that component that's parallel to x1. So the second that I made a mistake, all of a sudden now my eigenvalue iteration algorithm is like super excited. It's like, oh, there's this number here, I can make it bigger and bigger and bigger and bigger, and eventually that numerical error is going to drown out what you were really looking for, right? Like the second biggest eigenvalue. Well, how can we get rid of that? Well, we know that during each iteration of power iteration in step 3 here, for example, right? During every single iteration, A times X should not have a component parallel to X0, because we projected it out, yeah? Now we can do it, there's no way to get it back. So what we do is just explicitly at each iteration, project out X0 again, right? And that way, this sort of removes this numerical drift issue, right? So one way to think about this is if you think of P as this projection matrix that just removes the span of the eigenvectors that you've seen so far, right? Then you can think of our next our next go at power iteration is actually doing power iteration on P transpose AP, right? Where this thing is just projecting out that eigenvector at each iteration. Do you see how this actually has some meaning, right? You should think about this as, okay, well, if you write down P transpose AP, the P on the right-hand side is just projecting out the stuff we've already seen. Then I apply A, just like before. And then for fun, I project it out again. Remember, P is symmetric for orthogonal stuff. Yeah? So, in fact, what are the eigenvalues of P transpose AP? By the way, the fun fact. The eigenvalues of A except what? All of the eigenvalues that we project out in P go to 0. Do you see that? Because now, if I multiply P transpose AP by x1, right, like that first eigenvector, what happens? Well, P times x1 is 0 by definition, right? I project that guy out. And then it doesn't matter what happens, yeah? So basically, what did we do? Well, we played the same game we already played the last couple times, right? We took our matrix A and we modified it, this time by pre and post multiplying by projection, right? And then when we did that, what happened? Well, now we had all the same eigenvalues except the ones we've already seen are now small, but since we're trying to find the biggest eigenvalues, we're good. Yes, Scott?
Why is it P transpose AP as opposed to just AP?
So P is equal to P transpose. So in fact, this is just P. We write it in this way for something to see. So that's a good catch. Right. So in general, this strategy is called deflation. Right? What did we do? We took A and we deflated it. We removed the eigenvalues that we didn't like and we just moved them to 0. And then we ran power iteration again. Yeah? And this is sort of state-of-the-art in eigenvalue iteration. So, let's step back. So in the end, we do want to have strategies for asymmetric matrices and so on, right? So we have to be a little careful about how we deflate. And our deflation algorithm so far, as we kind of talked about, doesn't work so well when your eigenvectors aren't orthogonal anymore. So we need to take care of that case. So to do so, we're going to introduce one additional sort of mathematical formalism. So we're going to say two matrices are similar, right? So A and B in this case are similar. If there's some invertible matrix T, so that if I pre-multiply by the inverse of T and post-multiply by T itself, I go from one matrix to the other. Right? We have to remember when we talked about diagonalization on Monday, that is an example of similar matrices, right? A symmetric matrix is similar to the diagonal matrix of eigenvalues. Yeah? So, right, where's my eraser? Here. In particular, we can prove one really handy lemma, which is going to get us back. Remember, and so I'm trying to help you guys develop patterns in CS205, right? One of the patterns is this sort of strategy of using elimination matrices, right? That you think of operations that we're doing as really just multiplying by some simple matrix. And so I'd like to be able to apply sort of similar thought process to the eigenvalue problem, because I want to use the same hammer. And to do so, we're going to need one small lemma, or proposition, I guess, which is that similar matrices have the same eigenvalues. Right? And why is that? Well, let's say that A x, did I do this right? No. Let's say B x is equal to lambda x. Right? What does this tell you about life? Well, in particular, it tells you that T inverse A T x is equal to lambda x, right? Just by substituting our expression for B. Yeah? And so let's multiply both sides by T inverse. So we get A T x equals lambda T x, right? So in particular, this vector is an eigenvector of A. Right? So this shows that they have the same eigenvector. This is easy to go in the reverse direction. Yeah. Well, this gives us a strategy now that sort of looks like our Gaussian elimination game, right? What can we do? Well, we can transform our problem by applying any similarity transformation we want. We start with A and pre-multiply by some guy inverted and post-multiply by the same guy. And we know that we haven't changed the eigenvalues, right? And if we can just keep doing this until we get to a form that's easy to deal with, then we're golden, yeah? So in particular, we don't have that many options of matrices that we know how to invert easily. And one of them is this householder matrix that we dealt with 2 lectures ago. Remember, householder matrix is a matrix of a reflection with a minus sign in front. And by the way, since I made a couple sign mistakes in lecture, your first homework problem this week is basically doing my proofs from lecture without sign mistakes. Which should be easy for you guys. And means that if I hear an excuse on your midterm, like you did it wrong in class and thus my answer was wrong, it doesn't hold up because you're doing the correct thing on your homework. Just because your instructor is stupid doesn't mean you have to be. Okay. So in particular, let's say that I take this householder matrix and I choose a householder matrix H. Remember, this is some reflection, so that if you take the first eigenvector x1, you get back E1. And in fact, the problem 1c on this week's homework shows that you can always do this. That given this, like 2 vectors like this, there always exists some householder matrix that reflects this guy in it. It's sort of reasonable that should be true. Yeah. Well, let's do a little bit of math. In fact, I guess I conveniently wrote it up here for myself, so I don't even have to do it on the board. Yeah? So what happens if we multiply? So first of all, remember that H inverse is equal to H transpose? Yeah, remember this fact from a couple lectures ago? If not, it's also on your homework. So that means that this thing is effectively conjugating by H, right? It's doing a similarity transformation by this matrix H. I just wrote it in a funny way. And let's say that I do this and I multiply it by a vector E1, just the first identity basis vector. Right? So 1, 0, 0, 0, 0. Well, first of all, householder matrices, if you recall, are symmetric. So this, I get rid of the transpose of H and just say this is HAH times T1. And then, what do we do here? Well, we want to know what HE1 is. So far we know HX equals E1, right? So then in particular, X1 is equal to H inverse of E1. Right? But remember that H sort of looks like a reflection, right? And if you reflect something forward and then you reflect it back again, even if I made a sign mistake, and then you get back to where you started. So we know that H squared equals I, which is the same as saying that H inverse equals H again, right? So if I apply H twice, I get back to where I started. Yeah. So in particular, this means that this is the same as HE1. Yeah. So if we read this backward, right, then HE1 is x1, and that's what I've applied here. Now, what is AX1? Well, x1 is an eigenvector by definition, so we can plot this lambda 1, and we just have HX1 again, and then by our choice of H, we get E1 again. So in particular, what did I just show you guys? I showed you that the first identity basis vector, right, E1, is an eigenvector of HAH transpose with eigenvalue lambda 1. Yeah? But I also showed you something else. Remember, there's a trick for writing down matrices, the action of a matrix, where you can say, well, what is a matrix M? Well, he's equal to M times the identity matrix, for sure, right? And this is M times, remember, E1, E2, and so on. Yeah? And remember, how do I do matrix products? It's the same as ME1, ME2, and so on. Yeah? So in particular, the first column of M is nothing more than M times the first identity vector, right? So we showed that the first column of HAH transpose is this guy, right? So let's write out what this looks like. Looks like that, you know? So the first column has got lambda 1 and then a bunch of zeros, okay? That's what we just proved. And then the rest has, well, we don't know what, but something. Yeah? But what do we know about the eigenvalues of B? The lower, right, this lower square inside of our conjugated matrix. Well, how do we get to HAH transpose? Well, we got there from A by conjugating with this matrix H, right? By doing a similarity transformation. And we know that similarity transformations preserve eigenvalues, right? So the eigenvalues of B have got to be the eigenvalues of A, just with lambda 1 removed, right? And you can see that because there's a lambda 1 with a bunch of zeros, right? So clearly there's an eigenvector here, which is just E1. And if you remove that, you got the rest. Yeah? So this is a really slick strategy for finding all of the eigenvectors of a matrix, right? What do? Well, I find the first eigenvector x1, right? And then I find this householder matrix H, and I pre and post multiply by H, right? Get rid of the first row in the first column, and then find the biggest eigenvector with this new matrix B, and repeat, rinse and repeat, so you get down to a 1-by-1 matrix. Yeah? And this works for asymmetric, right? There was nothing about my proof that had anything to do with symmetry here. So in fact, this deflation strategy works regardless of whether A is symmetric or not. Yeah? So this is a nice strategy for finding all the eigenvectors of a matrix. Cool. In fact, in decreasing order. Yeah, so you're just going to do power iteration on B, and then recursively, right, you can apply the same trick to B, and then remove another row and column. Cool. Now, this algorithm is a little bit weird in that, I keep saying that today. This algorithm is a little strange because you only get one eigenvalue at a time, right? And so each time you do this, you have to, once again, run power iteration. Power iteration might take a long time. And a natural question to ask is, can I sort of get more than one eigenvalue and eigenvector in parallel? Right? Or am I stuck just doing this one at a time? Right? All the algorithms we've done so far just do one at a time. And in fact, you can do them in parallel, and we're going to cover one algorithm which I should warn you, I'm super enthusiastic about. This is like my favorite algorithm in the world because it's just beautiful. So we're going to start it today, and it looks like we'll probably finish next time. This is an example of a Krylov subspace method, which obviously makes it a beautiful algorithm. Okay, so remember our strategy, sort of at a high level, right? Was that if we take matrix A, and we conjugate it, right? When I say conjugate, I mean pre-multiply by something inverse and post-multiply by that same matrix, yeah? But not inverted. And we proved that A and the conjugated A have the same eigenvalues, right? So if I can somehow keep conjugating A until I get something diagonal, right? The eigenvalues of a diagonal matrix are pretty darn easy to read off. In fact, the eigenvalues of an over triangular matrix are pretty easy to read off. Yeah? So what we don't really like is we don't want to have to keep applying inverses of matrices to conjugate, right? That's going to be pretty inefficient because like our question, right? Here we're applying Q inverse to an entire matrix A, which is n by n, right? So somehow that actually is equivalent to inverting Q, and that's not a nice thing, right? Like if A were the identity matrix. So what can we do? Well, what matrices are easy to invert? Well, we talked about this when we talked about QR factorization in column spaces, right? In particular, orthogonal matrices have this nice property that their inverse is their transpose. Right? Remember orthogonal matrix? That's the one where all of the columns are orthonormal to each other. Yeah. So kind of an interesting strategy, one that we already saw when we deflated with this householder stuff, right? Is that we're going to conjugate our matrix by a bunch of orthogonal guys because orthogonal guys have nice inverses. Yeah? But sort of the natural question that we should be asking, which isn't as clear as for Gaussian elimination, is specifically what orthogonal matrix should we conjugate by? And what I mean by that is, like, if we look at our list of orthogonal matrices we have so far, in fact we only really have one, right? We have this householder reflection. But it's not really clear how to pre and post multiply by a householder reflection in a way to get a matrix into a nice form. At least not to me. Of course, numerical analysts no doubt have considered every possible case, and probably very easily. And in fact, if you look at Gibbons rotations, some of these other strategies we don't cover in 205 that are in your textbook for QR factorization, you'll see it's not 100% clear how to go from this conjugation trick to a nice eigenvector form. But we could do a little bit of science here. So if we have a matrix A, there is one orthogonal matrix that we could just play with a little bit, and that's we could factor A as QR. Right? So remember, Q has a basis for the column space of A. So Q has something to do with the structure of A. It doesn't necessarily have anything to do with the eigenvalue of A, but it has something to do with the structure. Right? And a natural thing you could ask is, well, what happens if we conjugate by Q itself? And this is just so magic. Like, and this is where, as far as I can tell, the only way you could come up with this algorithm is just by experimenting with, like, well, what's a reasonable orthogonal thing? And this is one. Yeah? So what happens? Well, we have Q inverse A Q. Yeah? What is Q inverse? Well, we know that it's the same as Q transpose, right? Because Q is orthogonal. Yeah. What is A? Well, we factor A as QR. That. Now let's group this way. What's Q transpose Q? Well, it's the identity matrix. Yeah, it's just I. So in fact, if A is QR, then conjugating A by Q is RQ. Right? And you look at an expression like this, and sort of from a philosophical point, you see, like, this has got to be something very fundamental about life, right? Somehow these guys commuted, and that shouldn't just happen by accident. So in fact, Justin's favorite algorithm in the world can be written in 3 lines, which is you start by defining A1, this is your matrix A, and then what you're going to do is you'll factor your kth matrix as QR, and then you're going to replace that with RQ. And then you're just going to iterate over and over and over again. And it turns out, at least when A is symmetric, that the matrix R will converge to a diagonal matrix of all of your eigenvalues. And the matrix Q will converge to the orthonormal basis of all your eigenvectors. This is amazing. Like, this is like the world's most beautiful mathematics, right? Like, this is, and it's like a synthesis of the last 3 weeks of stuff that we've done. So we're going to spend a little bit of time. We'll start today proving why this should work, and probably on Monday we'll finish it off. It's not on your homework, don't get upset. Okay. So the first question you might ask is, never mind whether it converges, what happens if it did converge? Right? So, like, what happens if I keep running this QR iteration, and eventually this thing settles on, I keep getting the same matrix A